Hey everyone. Um, Today I'm going to be reading this book called Reinforcement Learning: An Introduction by Richard Sutton and Andrew Barto. This is a book written by the pioneers of reinforcement learning. And my plan is that I'll be reading the book and implementing all of the algorithms within the book. And I'll also be taking notes side by side and publishing them on my Notion later on. I hope that at least someone will find these useful. So, yeah, let's jump right in. Let's go to the introduction first. So, in the introduction, the authors are mostly talking about what reinforcement learning is and how is it different from supervised and unsupervised learning. The basic idea in reinforcement learning is that there's an agent, and the agent is interacting over time with an environment, and it's trying to achieve a goal. So this is the basic setup of the problem in reinforcement learning, that you have an agent which is within some sort of environment, and there's a goal. So these are the most important things. The agent is also able to sense the state of the environment. So it has a sort of input, and it's also able to take some actions which affect the state of the environment. So these actions are basically like the outputs. The way this is different from supervised and unsupervised learning is that in supervised learning, you basically uh, get to know the correct action to be taken in each situation. So, for example, if you have a state S1, then you are basically given a set of examples to learn from. So, you have a state S1, and you know the correct action should have been A1. And for state S2, you have a correct action A2. And the basic problem is to extrapolate or generalize to a new state. So given a state S dash, what is the correct action to be taken in this state based on the previous examples? So that is what supervised learning is about. And unsupervised learning is basically about finding some hidden structure in the data. So, for example, you might be given a data set and you want to say cluster it or find some internal hidden representation. So that's unsupervised learning. But in contrast, reinforcement learning is mostly about planning and taking actions, and the action can also affect the state of the environment that you are in, and it's basically a very general problem. Uh, and the idea is to be able to achieve any goal. So this is what the reinforcement learning setup is. The main challenge in reinforcement learning is described here, uh, a trade-off between exploration and exploitation. The idea is that if the agent keeps taking the same action each time, even though it might be a good action, but it will never like explore other actions which might have been better. So that's the trade-off between the exploration and exploitation. Another key problem is that we are dealing with an uncertain environment. The environment may not even be deterministic, and all the other approaches of machine learning, they basically consider the sub problems. They do not tackle the whole problem of, uh, let's call it, planning and uh, like solving a goal directed decision making kind of thing. Um, then there are various examples of reinforcement learning described. For example, chess can be viewed as reinforcement learning. A petroleum refinery's operation can also be controlled by some reinforcement learning controllers. Biological systems like the gazelle and someone preparing his breakfast could be also considered reinforcement learning, because there's a goal, there's an environment, and you take actions to achieve the goal. The main elements of reinforcement learning include a policy, which is a map from the state to the action, a reward signal, which is sort of which defines the goal for the agent, and a value function, and optionally a model of the environment. So this value function thing is pretty important, I guess. The value of So basically, you can imagine that the reward signal is like a pain or pleasure. So in a biological system, you could think of a reward as analogous to the pleasure or pain. However, that is the immediate pleasure or pain. But in general, what we want to do is to maximize the long-term reward. So you want to maximize pleasure in the long term, even if that means suffering from pain right now. So we define a value function. The value function uh, spe- describes the total amount of reward that can be expected to accumulate in the future. So you can say that the value function is basically like the expected total reward from this state to the end of this to the end state. So that's these are the basic definitions. There is also a optional model of the environment which you might or might not have. Some reinforcement learning algorithms are model free, which are like the simpler methods, whereas some methods are model based methods. Um, we also distinguish reinforcement learning from evolutionary methods. So in the case of evolutionary methods, we have a policy, and various changes to the policy are made, and like uh, these are basically evolved in a way like the um, all of the organisms, you can say, are tested for fitness, and the policy which is like more which performs better gets copied and so on. However, these ones are different from reinforcement learning in such a way that reinforcement learning considers this from the organism being born till it's dying. There are many states it passes through in between. Uh, in an evolutionary algorithm, it would not consider the intermediate states at all. The effect whether the organism passes on to the next generation or not depends on uh, the entire history of rewards. However, in reinforcement learning, you would also consider the individual states that the organism passes through. So you can also learn within a single episode in reinforcement learning, but that is not possible in evolutionary algorithms. Further, we are talking about uh, an extended example of tic-tac-toe and a certain uh, algorithm called as temporal difference algorithm or TD learning. So in this algorithm, so here we are talking about the game of tic-tac-toe. I hope you're familiar with the game. Uh, however, like there is a well-known algorithm called as the minimax algorithm in game theory, which we can use to find the optimal way of playing this game of tic-tac-toe. However, the thing is that that algorithm always produces the optimal result. In the case of tic-tac-toe, the result is always a draw, the optimal result. However, it is possible to win against a weaker player if we know that the player is weak. We can perform a non-optimal move, which can actually lead us to winning. So, if we assume that the opponent is imperfect, using reinforcement learning, it is possible to play better than the minimax algorithm. Now, the question is how will we do it using reinforcement learning? So, a very simple algorithm is described here, which is called as TD learning algorithm. So, first of all, we set up a table of numbers. So, this is the table of numbers that they're talking about. We have one number for each state. For each state of the tic-tac-toe board, we have one number, which is the value function. This value function tells us the probability of winning from starting from that given state. So for a state like this one, uh, the value function would always be set to 1, because in that case the player has already won, and the value function can be set to 1. In the case that the player has already lost, the value function can be 0. In all other cases, initially we will set all of the other values to 0.5 to indicate that the chance of winning is 50%. This would be the initial guess from which we start the algorithm. After this, what we would do is like we'll start playing with the opponent. We'll play many games, and for each game, we will be doing two things. We will Most of the time we will move greedily, selecting the move that leads to the greatest value. So so this is something called as a alpha greedy sampling method. So in a alpha greedy method, let's say that we have a number called as alpha. Let's set it to zero point 0.1 in the starting. So what this means is that with the probability of 1 minus alpha, so 90% of the times, you would choose the state with the greatest value. So for example, if you have a choice between these three states, you would always pick this state with the zero point 0.9 value. However, with the probability of alpha, so with the probability of zero point 0.1, you would choose a random state. So you might choose this one or this one, or even this one. So with all of these with probability 1 by 3. So just to summarize, like in the starting, you have two choices. First with probability alpha, you choose a random state, and the second with probability 1 minus alpha, you choose a greedy state. So the one with the maximum value. So these random moves are called exploratory moves, and they happen with probability alpha, and all of the other are the greedy moves. Now, what we will do? Initially, remember that the value table looks like all of the states are either 0, 1, or 0 0.5 for the unknown states. Now, this is the initial guess, but we want to improve this guess. So, to improve this guess, we have the TD algorithm, and what it does is that after each move from our end. So let's say that we were on the starting position, our opponent made a move, and then we made a move. This was a greedy move, and after each greedy move, what we will do is that we will update the value of the initial state. The way we'll update this is that we will add the delta of the value. That is the difference between this value and this value, and we will use this delta to update the value of the starting position. We will multiply it by another constant parameter. We can call it alpha, or we can call it anything else. This is different from the alpha that I talked about earlier. Um, this can be considered as the learning rate. So, uh, given this given this learning rate alpha, we will update this value at state t to be value at state t plus the delta between state t plus 1 and state t, and we will update it using this formula basically. Now, it is described here that this above method performs quite well on the task, and if the step size parameter is reduced properly over time, then it can be proven that the method converges to the value for optimal play, and it will always perform optimal move against this imperfect opponent. So given certain conditions of reducing the step size parameter appropriately over time, this method will converge to optimal play against a fixed opponent. Um, so this is the temporal difference algorithm that is described. We could try to implement this. However, there was a interesting problem that I saw described within the examples, which I think I will actually start my implementation with that. So this is the problem that's described here. Exercise 1.1 self-play. So supposing that instead of playing against a random opponent, what would happen if the reinforcement learning algorithm described above played against itself, with both sides learning using the same algorithm? What do you think would happen in this case? Would it learn a different policy for selecting moves? Now, I have two guesses here for what will happen. I think that one of the possibilities is that this algorithm could converge to optimal play. So that's one possibility, optimal play. Another possibility that is that maybe it does not properly learn. Maybe because both sides are changing their policies, it might not even converge. Could spiral and blow out. I don't know. That could happen, but there's only one way to find out, and the way is to implement the algorithm and to see what happens. So I guess we'll start with that. Let's try to implement this and see what happens. Hey guys, so I have finally implemented the code that I was talking about last time, and let's take a look at the results. But first, I think let me give you a brief overview of what the code does. So we have a random agent and a TD agent in this code, and they are playing against each other. And we are trying to make the TD agent learn to play tic-tac-toe using the algorithm that was described in the book, which basically updated the value function, and it was basically a tabular method to learn the value function. So what we have here is we have this class TD agent, which has this map self.value function, and there's the select move function. What the select move function does is that it firstly, it has some probability of making an exploratory move, but if it does not make an exploratory move, then uh, it makes a greedy move. The way it does is that it looks at all the possible states after making the move, and it looks up the value function for all of those, and then it selects the move with the highest value function in this line, and that's the greedy move. And it basically makes the greedy move, and it also notes down that the previous move type was greedy. I have also implemented a small metric library. What this metric library is basically doing is that it keeps track of some counters and some metrics, and it exports them into JSON. And I have a small Flask-based server and a dashboard. And basically, I use this dashboard um, to visualize the metrics which are generated by the algorithm. So, um, so yeah, I after this select move function, I also have a update reward function. So basically, what the algorithm is supposed to do is that it makes a move and according to some to the greedy choice, and whenever it makes a move according to the greedy choice, it basically updates the value function of the starting position based on the value of the ended of the end position. So this is what the update reward function does here. It basically has an old state and the new state, and it basically compares the values of the old state and new state, and it calculates a delta. This delta is called the TD error, and it's multiplied by a certain step size, and it's added into the value function of the old state. So this is sort of the step which back propagates this value function from the terminal states to the starting position. And this is basically the function which selects the value of the final states. The sort of this function does two things actually. It first of all looks up the value function for any given state, and in case it is a terminal state, then it selects the correct value for that state. So what we have here is this TD agent, and this TD agent is playing against a random agent. So let's see what happens when the TD agent plays against the random agent. So I'm running main.py, and it's playing a lot of games. We'll have to wait a bit for this to finish. It's going to play, I think, 10,000 games. And after 5,000, right now the parameters are set such that the probability of making an exploratory move is 0.1, and the step size is also 0.1. But after 5,000 games, the exploration probability will be set to 0. And it's also exporting these metrics like the number of episodes, the outcome of the games, uh, and the value of the old state, new state, and the delta between the values. So let's just wait for this to finish. And then so in the meanwhile, I'll also just let you know that I've used GPT-4o for generating some of this code. This is mostly boilerplate code. For example, the code to handle the tic-tac-toe state, and uh, for this metrics and dashboarding library. But the main TD agent code I have written on my own so that I can get a deeper understanding of what's going on here. And while I was writing this code, I also faced certain bugs. One of the main bug that I found was that was based on a little bit of a misunderstanding of this algorithm. So there's one interesting thing in this algorithm that I did not notice at first. That is that the position whose value we are updating is actually the position where it is the opponent's move. It is not this position whose value we are updating. we always need to update this layer of positions, the value of this layer when it is the opponent's turn. This is because when we are selecting a move, we would like to look at the values of these states. If we instead update the values of these moves, then these values would always be zero point 0.5, and we would never be able to select the correct move. So that was an interesting observation and a sort of bug that I had in my previous code. Uh, but now I have fixed it, and uh, yeah, and let's just see if the code finished running. Yeah, it did. So let's see what the final outcomes are. First of all, the random agent has won 1000 times. The TD agent has won 7600 times. And the game ended in a draw almost 1000 times. So it's almost like 76% of the games are being won by the TD agent. So the algorithm is definitely working. Let's look at the metrics. So I started this dashboard server, which runs using Fast. And let me just go here and look at the metrics. So some of these metrics are irrelevant, but let's look at these outcomes. So this is where uh, so this metric actually shows that the TD agent is winning far more times than the random agent, and this is denoting the draws. Uh, and if we look at the random agent, like the number of times the random agent is winning, it does win quite a few times, but the rate at which it is winning games is constantly decreasing. So this is basically a cumulative metric. I should have added a delta mode here, but I didn't just yet. But anyway, we can look at the sort of the slope of this graph, and we can see that the rate at which the random agent is winning games is definitely reducing. And it does seem to reduce quite a lot when we switch off exploration around here, around somewhat here in the middle. So that shows that our TD learning algorithm is definitely working, and this is the R and the S values. Now, because the R and S values are generally zero point 0.5 or 1, so what we can do is like we can try and smooth the graphs a little bit so that we get a better idea of what's going on in the average behavior. Right. So looking at the smoothened graphs, what you can see is that the that both R and S values start at almost zero point 0.5, and they slowly increase as the TD agent is learning. I think that seems to indicate that our TD agent becomes more confident about winning as it is learning. So like the starting position generally tends towards this value of zero point 0.8 or 9. So that means that our TD agent on average is around is around 85% confident in its chance of winning. This is the TD error. It starts out at a higher value, but it slowly converges almost to an average value of 0, which seems to show that uh, the agent becomes more accurate at predicting the expected probability of winning. So, so yeah, that was the DD learning algorithm that was described in the book. Now, the book also had an interesting question: what would happen if we allow this algorithm to self-play, to do self-play? So what would happen? And I had guessed that it would converge to optimal play. So let's try to see what actually happens in this case. Uh, I've written another script called selfplay.py. This script has both TD agents, and it will play one agent against the other. And let's see what happens when we run this one. Okay. So the TD agent uh, self-play script has finished running, and what we see here is in the final outcomes is that the TD agents won against each other around 1600 and 800 times. Uh, but the number of draws was around 7500. So what that means is that most likely these agents are tending towards perfect play against each other, and most of the games are actually ending in a draw. Let's also look at the same metrics once again. So I'm going to select just a few of these metrics here. So what we see here is that once again, uh, the number of draws is almost 75%, and the two agents are, although they do win a few games against each other, but after the exploration is switched off, the number of games that they win against each other is almost reduces to zero, and the the value of the metrics, like the final state and the starting state that we were tracking, almost converges to zero point 0.5, which is sort of expected for the optimal play. The value of TD error is also looking like it converges to zero once exploration is switched off. So yeah, what we can conclude from this is that uh, when two of these TD learning algorithms are playing against each other, when they're playing both sides, it does seem to converge to optimal play. So yeah, that was all for now, and I'll continue with the rest of the book in future videos. And this was just an introductory algorithm, I think, and it was not even mentioned as TD learning. Uh, Although the actual TD learning algorithm will be discussed later in the book. So let's continue in the next video and see what else is there in the book. So yeah, thanks for watching, and I'll post all the sort of updates and the link to my notes to my Notion site and uh, to this code in the description. And thanks for watching. See you next time.